In number theory, we encounter a strict barrier when trying to mix additive operations, like a plus b equals c, with the multiplicative structure of prime factorization. This is the ABC conjecture. It states that for any three co-prime positive integers, their maximum value is strictly bounded by the radical of their product, raised to a power slightly greater than 1. Because standard geometry struggles to measure this tension, we translate the integers into a Frey elliptic curve over the rational numbers. The mapping is precise. The integers a, b, c squared define the curve's discriminant, while the radical, the distinct prime factors, becomes the curve's conductor. Converting these numbers into a geometric curve provides a physical terrain where we can rigorously measure and restrict mathematical anomalies. If the ABC conjecture were false, a sequence of trios could grow exponentially out of control. This flowchart maps the impact. The Frey curve develops an ultra-deep geometric stretch. Variational flow fails to converge, creating an infinite curvature spike at the ramified primes. This anomaly must be reconciled with the global functional equation, which enforces macro stability across the Adel ring. But here is the failure mechanism. The geometric stretch causes wild swan conductors to explode toward infinity, shattering the functional equation and preventing scale inversion. Because a counterexample inherently destroys global reciprocity, the system requires a local mechanism to strictly cap the geometric distortion of the Frey curve. To find those limits, we look at the prime p equals 2. This canonical Tate shift standardizes the two adic valuations of our curve. By applying this substitution, the minimal discriminant drops by a factor of 2 to the 12th, allowing us to isolate the true conductor exponent. Consider a case where the variable b is heavily divisible by 2, specifically b modulo 16. Using Tate's algorithm, what happens to the wild swan conductor in this semi-stable branch? As the table shows in case A, high divisibility forces the reduction to become multiplicative. This causes the wild swan conductor to vanish, locking the total conductor exponent at exactly 1. This local stability is represented by the Steinberg representation on the hecastack. These Satake parameters reflect the unipotent architecture of the multiplicative reduction. When run through the trace formula, a while bounds strictly pin the active eigenvalue to p to the negative 1/2. This architecture acts as an unbreakable cage. It structurally prohibits the local field from developing the exponential divergence required by a counterexample. In spectral geometry, these mathematical bounds have physical consequences. Using the Kahn's-Chamisidine principle, the physical mass gap is calculated via the global L function. This isolates the mass shift injected by prime factors. Because eigenvalues are pinned to the Steinberg core, the denominator grows rapidly, forcing the summation to remain finite. If the ABC conjecture failed, the mass gap would explode, preventing stable coordinates from forming. With the ABC bound imposed, the shift collapses into a highly stable convergent constant. This bound is enforced by the Fourier-Mukai transform. It harmonically distributes divergent energy across the cycles of the prim variety, creating a rigid geometric envelope that protects the global functional equation. By locking the local L function eigenvalues to the Steinberg core, the system pins down stable, fault-tolerant mass coordinates. This proves the ABC conjecture is an analytical requirement for physical stability across the Adelic ring.